today we will discuss more about error budgeting in analog circuit, because we had seen how to apply operation amplifier for resistance measurement, and then various transient signal conditioning like LVDT also we had seen, but we also worked out errors associated with the operation amplifier. We see the in a consolidated manner what are the errors that is coming in the operation amplifier and how to compute them in the real instrumentation design. So, we look at the operation amplifier errors and today's structure. Errors and error budgeting. So, we will see the errors involved are actually offset voltage drift, this we already discussed. We will see more about this, and then we will have bias current drift, or offset current drift, both we will look it together. Offset current drift, then we had actually gain drift error, this we have not discussed so far, gain drift error. Then we have input impedance, input resistance error, input resistance of the op amp that we should find out. Then we had output resistance of the op amp, then we had the errors due to common mode rejection ratio, introduced error. Then input resistance error, gain error. But so, these are the various errors which is there as far as DC signal is concerned. There are other errors which are associated with AC signal processing, that we will see separately at some other time when we are dealing with the AC applications of the operation amplifier. Now, we will see offset voltage drift error, and then why it is coming, then how to compute and make error budgeting, introduce in the error budget the errors related to the offset voltage drift. Now, if you look at our original op amp circuit configuration, that basically we see our 3 transistor op amp, that this is the circuit that we had. And this is acting as output, and this is the power line is a plus voltage and minus voltage, and the 2 inputs, plus input and minus input. So, we want to apply the amplify the voltage, we give the input here, and for example, if it is a voltage follower, we directly connect this to the output. This is a voltage follower, that is whatever voltage input is given, and the same thing appears at the output. So, V input is equal to V output. Now, in this case, the basically the operation amplifier was working with the assumption that the voltage drift, the base emitter voltage here and the base emitter voltage here VBE1 and VBE2 are same, and with temperature also they are tracking always equally. So, that is one of the basic assumption that is made in the operation amplifier design. So, the base emitter voltage of the input transistors are identical voltage are same in the sense that the, say over a temperature over a working temperature range. But in reality that base center voltages may not be equal, and if they are not equal at that temperature we call it as offset voltage. But then the difference also not constant, the difference varies with the temperature, that we refer it as offset voltage drift. So, the delta VBE is considered as offset voltage. Offset voltage is not a series issue that can be compensated out. Then delta VBE change with temperature, is called offset voltage drift. Offset voltage drift. Offset voltage drift is one which is very serious, because this cannot be compensated normally without using additional circuit, because offset voltage can be compensated by adding a reverse voltage to the op amp, and that problem can be solved. But if the temperature offset voltage changes the temperature, then output changes, and that creates a problem. That is what we had seen earlier in the case. Now, for example, we take a simple circuit, for example, thermocouple amplifier I want to make with operation amplifier. Then, for example, we have a thermocouple, single junction thermocouple connected to this. Then we have a gain that we said, we have a gain RF by R1. So, the this gives us this is V in, and then this is V out. Then V out actually is given by V in into gain, and that actually we had shown as 1 plus RF by R1. So, this equation I leave it to you, that you can find in very many textbooks how to derive this equation. So, we get a gain in this. So, by for example, if thermocouple voltage, if we take is a single junction thermocouple, the range is, its sensitivity of thermocouple is the thermocouple is 40 microvolt per degree C. So, in this case the it produces a temperature difference depending upon I will redraw this so that it is convenient to look at it. For example, we can have a sensor terminated in a block like this, then this is grounded. Now, the temperature difference between this junction and this block, so this is T1, T2. So, thermocouple produce a voltage corresponding to the temperature difference between T1 and T2. So, T2 is the terminating block. So, the thermocouple voltage, output voltage is T1 minus T2 into sensitivity, that is V0. So, by taking the difference in temperature, so we can get the output voltage. For example, if T1 minus T2 is say 50 degree C, and then sensitivity is actually, for most of the thermocouple it is roughly 40 microvolt per degree C. So, then V out actually comes 50 into 40 microvolt, that comes 2 millivolt. So, for 50 degree temperature difference, then we will have 2 millivolt as the input, and then if we take gain as 1 plus, taking gain equal to 25, that is equal to 1 plus RF by R1. So, by taking RF is equal to 24 K and R1 is equal to 1 K, one can get a gain of 25. So, that will give V output of the op amp as, so output of the op amp will become actually it will become 25 into 2 millivolt, that actually become 50 millivolt. So, this is what one can expect in the ideal op amp case. So, if it is ideal op amp, then if this is for example at room temperature say 25 degree C and this is at 75 degree C, then the temperature difference is between this and this is 50 degree, and corresponding to 50 degree this will put 2 millivolt, and 2 millivolt divided by multiplied by 25, that will expected to give 50 millivolt output here. This is what expected, and 50 millivolt supposed to be stable over the operating temperature of this op amp. It is assumed that the operation amplifier is kept in the working environment. So, and this is kept at the temperature where the temperature to be measured. This junction is kept at the place where the temperature to be measured, and the op amp is probably kept in room temperature because this is inside the instrument. But the room temperature changes, so the operation amplifier temperature also changes, and that actually makes this output to drift, because offset voltage of the op amp drifts with the temperature, because offset voltage changes with the temperature. As we discussed that base emitter voltages are not matched exactly for the two input transistors. Net result is we get offset voltage drift. So, for example, if we take 741, then we have for example for 741 op amp, offset voltage drift is given as plus or minus 15 microvolt per degree C max. That is the maximum drift expected to be 15 microvolt per degree C, and it is not exactly 15 microvolt, and the polarity also not known. It can be plus or it can be minus, or for some op amps it can be even 0 within 741 IC itself. So, when we make this instrument, we do not know what is the drift of the op amp that what we are using. If I am using 741, then it is not known. For this particular piece of 741 which I am using has how much temperature drift it has, it is not known. So, one have to take always the maximum value. So, if in this case it is 15 microvolt per degree C. So, for ambient temperature variation of minus 20 degree to plus 80 degree C. This is the range at which industrial grade equipment supposed to work. So, the equipment the room temperature may be anywhere from minus 20 to plus 80 degree. This is coming because this instrument in industrial environment might be installed straight away in the open air where sunlight falls, or the ice also drops over the instrument. That is why industrial grade equipment supposed to work in this temperature range. So, if you are using for industrial application, then I had assume 100 degree variation as the temperature change. So, in that case, if the 100 degree variation is expected, then total offset voltage drift to be calculated to be 15 into 100 microvolt. So, total offset voltage drift would be 15 into 100, that will be 1.5 millivolt, which will be plus or minus. So, the at the input we can expect 1.5 millivolt change because of the offset voltage change. That means, at this point you can expect 1.5 millivolt change due to offset voltage drift alone. So, that puts an uncertainty, because that offset voltage supposed to be added with the input voltage, and then we should calculate what will be the output. So, if I add the signal is 2 millivolt, offset voltage is 1.5 millivolt, offset voltage drift is 1.5 millivolt, then the total output will be voltage will be 2 millivolt plus or minus 1.5 millivolt into gain, which is 25. So, we will have, that means the error introduced by that is error due to offset voltage drift. Drift works out to be plus or minus 25 into 1.5 millivolt, which is 37.5 millivolt, plus or minus 37.5 millivolt. Now, if you look at this error, at the output of the op amp, 1 millivolt is 1 degree C, because we had seen it is coming 50 millivolt for 50 degree temperature difference. So, at V0 1 millivolt is corresponding to 1 degree error. That means, if I use 741 for this application, we will have error of plus or minus 35 degree. 35 millivolt, that is corresponding to plus or minus 37.5 degree error. So, the expected error at the output is equal to 37.5 degree C, plus or minus 35.5 degree at the output of the op amp, and this is quite large. Because the our signal is very weak. That means, offset voltage is a serious issue when the signal is input signal is very low, and in that case one have to go for low drift operation amplifiers. For example, we have LM714, we have LM07 and so on. There are various operation amplifier, the class of operation amplifier meant for low drift, meant for low level DC amplification. So, one had to go for low drift op amp. So, this error is large, for this 40 microvolt per degree C signal provided by the thermocouple. So, one if we had to reduce the error, then one had to go for so the what is to be done. So, go for low drift op amps. For example, we have a op amps drift as low as say for example, we have LM714 is there, LM07 is there. They provide offset voltage drift as low as 0.5 microvolt per degree C. 0.5 microvolt per degree C. So, this for example, if I had used this, then for 100 degree variation, the total input drift would have been only 50 microvolt. For 0.5 microvolt per degree C op amp, plus or minus op amp, the thermocouple amplifier error is equal to 100 degree ambient temperature variation into 0.5 microvolt. That actually gives you 50 microvolt error at the input. So, the total error will be total error is equal to 50 microvolt at the input. But at the input, that sensitivity is at the input signal sensitivity is 40 microvolt per degree C, it is equal to 40 microvolt per degree C. So, the total error in degree C would be 50 by 40 microvolt, that comes 1.25 degree C error. So, if I use LM714, then I will get error of only 1.25 degree due to offset voltage drift. So, that is why we have a class of amplifiers called low drift operation amplifier, and this is a very important thing one have to consider when you are designing a DC circuit, because one have to see what is the actual drift that is coming because of offset voltage drift, and this can be reduced only by going by the low drift op amp, because when you are making hundreds of units, each op amp that you are using will have different amount of drift. So, one cannot say what is the actual drift for a given particular piece. So, one have to take the worst case drift and then assume that is the worst error that I will get out of all these instruments. So, one have to go only for a low drift op amp, and there is no other no other thing that can be done to reduce the offset voltage drift. Of course, there are serious cases where the temperature, if the input signal is very low, for example, if you are using a sub microvolt DC signals that is to be amplified, and still we do not want the DC drift to be employed, then this can be housed in a oven. So, for very low level, very low DC signals, very low DC signals, then the option available is use oven, small oven like crystal ovens. You can have a very small size ovens available, and the front end alone can be housed in that. So, whatever circuit that you have, for example, if you are putting a input and stage, and this input stage alone can be housed, kept inside the oven, so that the temperature of this oven is maintained at constant say 70 degree, or if it is supposed to work at 80 degree ambient, then I go and keep it at 90 degree C. So, the oven is kept always at 90 degree. So, the ambient temperature will have almost no effect on the op amp, and the output of the op amp will not drift. This is one way of solving the drift problem if the signal is sub micro levels, because we do not have directly op amp which have very low drift, like maximum what you can get would be 0.1 microvolt per degree C drift. Beyond that we do not get op amp in the low drift category. Or other possibilities that go for chopper stabilized amplifier. Chopper stabilized amplifier, where you can expect the drift as much as 0.01 microvolt per degree C. So, here offset voltage drift will be very small, and these amplifiers can be used alternatively for dealing with low level signals. Of course, chopper stabilized amplifiers introduce a lot of noise. We will see more about this little later. So, the option that we have in case if you have to handle very low level signal is use oven and compensate it. But there are other techniques also being used, that namely that we can have auto zeroing amplifiers. That is, third option would be go for auto zero method. In this method, what is done is that you have an input signal. For example, the input signal is there connected here, and then connect this. Normally, what is done is that offset voltage of the op amp, you before, for example, if you want to make the output make measurement of this output voltage, what can be done is we can have a switch here, For example, I can have a switch and I can short this and make it ground. So, I expect 0 volt here, but then normally you do not get 0 volt, you will get the out when it is the input is 0, when the input is grounded, when the input is grounded, V0 is actually V offset into gain. That offset voltage changes with V offset changes with temperature. Changes with ambient temperature. So, before making measurement, initially you short this one to 0 and take this voltage, and this voltage can be stored say as X. Then open the switch say S, and then make the measurement, let that voltage be Y. So, the difference between these two X and Y gives you the input voltage. So, what is done is that step 1 is measure the output by grounding the input. Let it be X. Then second step is measure the output by opening the output by applying the voltage. Applying the input voltage, let it be Y. So, the X this is done all that time, so that X minus Y gives you the signal. So, before each and every measurement you have to ground it and see the output voltage, then apply the open the switch and see the voltage. That means, two measurements are to be carried out at each and every point. Every time when you want to make measurement, one have to do this, then the offset voltage can go off. This helps us to certain extent. If the drift is too high, even this technique will not work. If the drift is reasonable, then this technique works. So, obviously, one can see that in analog circuit we will be fighting most of the time against this offset voltage drift. This is one of the important problem, or one of the difficult problem one to crack in analog circuit design, particularly when you are dealing with the low level DC signal. So, one has to be aware how to calculate this offset voltage drift. Now, if you are having multiple stages, then mostly the input stage is the one you have to worry. For example, if I am amplifying a small signal, then if you have several stages of the amplifier, then second stage, for example, if it is a thermocouple amplifier, and then second stage again if I am putting another gain of 25, for example, here gain 25, another stage is gain 25. Then if this is a signal of 40 microvolt per degree C, and I can expect here 1 millivolt per degree C signal, here actually you get 25 millivolt per degree signal, because the gain here is 25. So, here 40 microvolt becomes 1 millivolt, the 1 millivolt becomes 25 millivolt here. Now, the drift of this op amp, second op amp, is not a big concern. The drift of the first op amp is very important, but not the second op amp. Drift of the first op amp is very important, and not the second one. Second op amp drift. This is because For the second op amp, the signal is now 1 millivolt per degree C. So, the maximum offset voltage drift, even if I take 741, the maximum offset voltage drift expected is 1.5 millivolt at this point. So, signal is 1 millivolt and the drift is 1.5 millivolt. That means the error expected here is only 1.25 degree. So, here I can use 741, whereas if I use 741 here, the expected drift is 1.5 millivolt at the input and the signal is 40 microvolt per degree C. This will equal to 37.5 degree error that as we calculated. So, the since the signal is amplified here, the second op amp drift is not a series issue, and again of course you have to see how much the signal is amplified. If you use the first op amp as a voltage follower, then even the second one's drift is drift matters. For example, if I had used in the first stage as a voltage follower, then we have to pay the price, because now the drift of both op amps comes into picture. So, because here signal is not amplified at all the first stage. So, the drift of this should be low. So, low drift op amp is required for this as well for this. So, both has to have low drift characteristics, then only the error can be controlled. So, one has to be careful that when we are using a voltage follower, that if it is a DC case, then we have to only if it is essential we have to use, otherwise we will be adding up the drift of this plus this, or we have to look for low drift op amp for this as well as this, because low drift op amp comes with the price that it costs more. So, one has to be careful in looking for low drift op amp. So, so one should be able to calculate for any given circuit what is the error due to the total error due to the offset voltage drift. This is an important spec. One has to work out various circuit models and see how much error that it is coming. For example, I can put one small circuit, for example, constant current source which we have discussed. For that we can find out what is the error due to the offset voltage drift. Like for example, if I have the circuit like this, so in this case offset voltage drift of this op amp will give a error, this drift of this zener will give a current error. There is a current source and this is Vz and this is plus 15 and this is R. So, you get this current I is actually Vz by R. So, the offset, the drift of this will directly affect this one. Similarly, if the offset voltage of this op amp drifts, that is to be assumed as if Bs is Vz is drifting, because offset voltage can be added like this, either plus or minus. So, offset voltage drift directly gives error. So, if the, for example, if it is 741, then if it is 100 ohm, then worst case current drift would be, worst case current drift would be 1.5 millivolt divided by R. For example, if it is 100 ohms, then that will come as, if we convert into microvolt, then you will have 100, that will be 15 microampere current drift is expected because of the offset voltage drift. And you may think that one can compensate this by putting a diode and so on. That is not possible, as we said that this offset voltage drift is not known for that particular piece. One for 1741 it can be even 0, another one it can be even plus 10 microvolt, per degree C. The third one it can be minus 20 minus 10 microvolt per degree C. So, the compensation is not possible for the offset voltage drift. So, one have to make error budget and make sure that the total error that is coming due to offset voltage drift is within the acceptable limit. That is the only solution that one can think of as far as offset voltage drift is concerned. So, by now it would have been very clear that offset voltage drift is a big bottleneck in the analog circuit design, and for DC circuit this gives a major this is a major source of worry for any analog circuit designer. So, next we see the other errors, that is namely offset current drift error or bias current error. Now, the bias current error is coming. If you look back our original simple op amp circuit, that we had this, then we had this, this is our output, and then this is plus, this is minus, and we have plus input here, and then this minus. For example, I connect this to this. Now, in this if you look at the base currents of this, there is a base current here and there is a base current here, this is a voltage follower. Now, this base current always is flowing into the operational amplifier. For example, this is a NPN transistor and there is always a base current. So, unless base current is there, the operational amplifier is not going to work, there is in this case the transistor not going to work. So, there is always a base current, and the base current of this and this base current of this, they need not be equal, and even if they are equal at one temperature, they need not be equal at another temperature. So, we define this the base current as a bias current. So, the base current of the input transistors transistors are called bias current. For example, if we take 741, we say the bias current, we say 50 by nanoampere. That is the current that is flowing, the base is in nanoampere range. This current is a must and it should not be blocked. If it is blocked, the operational amplifier will not work. For example, if you have a circuit, the operational amplifier circuit like this, you have the input. For example, I have want gain. So, I put the circuit like this, which should not be done. Connect this, then I put on capacitor and connect like this. So, this circuit will not work because the capacitor will block the bias current that is flowing to this, and the output will be always be saturated because through leakage resistance the current will flow and this point will climb up to a large value and that will force the output to saturate. So, this bias current is blocked. So, this is not acceptable, it is not acceptable. So, if I want to do this, then we have to connect we have to offer a path for the bias current. So, if you want, you can do like this. If you want, you can have the input voltage, and if you want to apply, so for some reason you want to block the DC component going here. For example, I may have DC and AC. If you want to block the DC, then I should use a resistance here for the bias current to flow. In this case, the bias current actually flows through this and then to the base of the transistor and then to the ground. So, the bias current actually now flows through this. Similarly, the bias current for this, for example, if the output is plus, if the output is plus, then the bias current actually goes like this, and then it goes and then into the ground. So, there are two types of op amp, that is if the inputs are NPN, then you have the bias current always flowing in. So, if the bias current in this case is always flowing in. If it is a PNP transistor the input, then the bias current will be always flowing out. For example, you may have a system like this, the input, for example, LM324 is having this kind of configuration, that input stage is actually is a PNP transistor. In that case, bias current is flowing out actually. So, in NPN transistor input op amps, op amps, and bias current flows, flows into the input. Most of the op amps are like this. For example, example 741 and so on, 741, 714, all this kind of most of the op amps are actually NPN type, and the bias current actually flows in. In PNP transistor input op amps, bias current flows out from the op amp. Like for example, LM324. So, the direction of the current, bias current, depends on the type of the op amp. It may be flowing like this, or it may be other way around. You may have minus plus, and the bias current may be flowing out like this. For example, this is LM324, this is LM741. Now, the question is, what is the problem with this bias current? Because bias current is an essential one, and without that the op amp will not work. So, there is always a bias current, and the bias current always flows either into the op amp terminal, or it flows out of the op amp input terminals. Now, the question is, what is the effect of this bias current, and it is another major worry for an analog circuit designer as far as accuracy is concerned, because the bias current also introduces a lot of DC error similar to offset voltage drift that we had seen so far. So, one had to be careful while designing the op amp circuit, and then one should make error budgeting considering the bias current introduced errors. So, let us take a simple circuit and see what effect that bias current is creating. You have plus minus here, then for example, I have no input signal, I have grounded the input for example straight away, then I have connected two resistors to give a gain here. For example, here RF and R1, I need a gain of say 25. Then if I put RF as 24K and R1 is equal to 1K, then I will get a gain of 25. Now, for example, I had put here 240K resistance, and here I put 10K, then I have the gain of 25. If assuming that offset voltage is 0, offset voltage is 0. There is no offset voltage, and then the input is 0. So, V in is 0. So, the expected V output also equal to 0. There is no offset voltage, but in actual case even though there is no offset voltage and even though there is no signal, the V0 will not be equal to 0, but in reality, but the expected V output is 0, but in reality, real life, V0 is not equal to 0. This is because that if you see the bias current for this op amp have to go. Now, the bias current comes like this, if the input from the output, it goes to the resistance and then it goes through this and then flows into the ground. That means through this 240k resistance the bias current is flowing. For example, if it is 741, the bias current is 50 nanoampere for IB minus equal to 50 nanoampere, then current through RF is equal to 50 nanoampere. So, voltage across RF, that is equal to 50 nanoampere into 240k, that comes 50 into 240 into 10 power minus 6 volt, that comes 5 into 24 into 10 power minus 4 volt, 120 into 10 power minus 4 volt, that is equal to 12 millivolt. That means, even though there is no offset voltage, I have taken an op amp which has 0 offset voltage, still I will get the output 12 millivolt. This is because bias current have to go through this, and without the bias current the op amp is not going to work. So, the error introduced by this with the offset bias current is 12 millivolt. So, the error due to bias current is 12 millivolt. For example, if I had used the resistance much higher resistances, for example, if I had used for the same 25 gain, if I had used, for example, here I can also go 2.4 meg and then 2.4 meg divided by 24, that comes 100k. This also gives me gain of 25, because that the gain again is equal to 25. But now the resistance what you are used is 2.4 meg. Now the bias current error is error becomes 2.4 meg into 50 nanoampere, which actually if you work out and see, you will soon will get 120 millivolt. It will be the because you will get 24 into 5 into 10 power minus 3, that comes 120 millivolt. So, the bias current error becomes more as soon as you increase the resistance value. So, if I want to set the gain, then I should not put any resistance I like. Higher the resistance that I put at the feedback, then higher will be the error. This error is irrespective of the offset voltage and offset voltage drift. This error is coming purely because of the bias current. Whereas, if I use for if I use a very low resistance, for example, if I use for RF is equal to 24k, then R1 is equal to 1k, then the gain comes 25, same gain 25. Now, the error will become offset voltage error, bias current error, actually you will have 24k into 50 nanoamps, that will come 1.2 millivolt. So, smaller the resistance, then bias current error will be lower. Now, we may wonder that why we worried only about one bias current, that is only the current that is flowing through the minus terminal alone we are worried, and we are never worried about the current that is flowing through the bias current that is flowing through the plus terminal. Now, the actually in this case the current is here also flowing through this, but then it is not developing any voltage because there is no resistance here, and because of that we are not worried about the plus terminal error. But if we have a circuit like this, for example, I have a circuit like this, then for example, I have a input, then I have a resistance here, then for the plus terminal bias current actually goes through this. For example, if it is a 10 millivolt signal and if I have 100k resistance, and then if it is 741, then the bias current actually goes through this. The bias current actually flowing through that will produce a voltage drop across this. So, as long as this is 10 millivolt, now voltage drop across this R. Across R would be 100k, that is number 5 into 50 micrograms, 50 nanoampere, sorry. So, that will come 50 into 10 power minus 4 volt, that is equal to 5 millivolt. So, you will have the 5 millivolt drop across this, that this will be higher, this will be lower, that means it is like this. Because the current is flowing like this, the current is flowing like this. So, this will be higher, this will be lower. So, eventually what happens is this voltage is subtracted. So, if I have here this voltage is now 5 millivolt. So, actually what you get at this point is not 10 millivolt, 10 millivolt minus 5 millivolt, you will get only 5 millivolt at this point. So, the operational amplifier, the op amp actually amplifies only 5 millivolt and not 10 millivolt. Now, that means the plus terminal bias current also introduces a error, and this error also can be large if the source resistance, for example, this 100k may be a source resistance itself, and this source resistance is high, then the error also high, or sometimes we add this resistance for protection purpose, because we do not want some large current flow into this. So, we add this resistance to limit the input bias current, input current that is flowing to the op amp. So, in that case this resistance introduces error. Now, we can see quickly that the bias current at the plus input produce a minus voltage, that is this whatever voltage that is developed is actually minus, in the sense that the input voltage minus this is what is appearing here, whereas in the earlier case when the current was flowing through the minus, that output voltage comes plus, because the extra voltage is coming. That means the bias current at the minus terminal produce a plus voltage, and the bias current at the plus terminal produce a minus voltage. That means that if I can show like this, for example, if I have the two circuits, if I have this and then input is ground, then I get V error, V0 is equal to positive, output will be positive. Whereas, if I have the same thing, then I have no signal, I connected this, then I connect this here. Now, the V output is minus voltage. So, the plus terminal voltage produce a negative error, and the minus terminal bias current produce a positive error, in the sense output is positive in this case, output is negative in this case. Now, one interesting thing that from this can emerge, that if we can combine this positive and negative, and if they are equal, then one can make the output equal to 0, that is the bias current error can be removed, provided the two errors are identical. Now, one possible solution for this could be like this. For example, I can have a circuit like this. So, how to combine both errors? How to combine offset the bias current error, at non-inverting terminal, inverting terminal with bias current error in inverting terminal. This kind of compensation is used very often in actual circuit. Now, what we can do is that we can put the circuit like this. I can have this, I can have this, I can have resistance here. Now, I have no input voltage. Assume the offset voltage is 0, then I can have the V output can be made 0, even though there is a bias current, because the bias current for the minus terminal is flowing like this and producing a positive voltage. The bias current for plus terminal is flowing like this and putting a minus voltage at this point. The minus voltage amplified by this will be the output. So, if this resistance and this resistance are correctly selected, and if these two bias currents are equal, if this current is equal to this current, then we can make the output go to 0. So, this kind of adjustment has to be done. So, by assuming I plus I bias current plus equal to I bias current minus, we can make error due to bias current to 0, by selecting the resistor values. Now, for example, if I want to have a gain 25, then I can select this RF and I call this as RB, such that this if they are correctly selected, then I can make the output voltage 0, and then it can the bias current error appears to be 0. So, we get calculate these values correctly, but that we will do in the next class. But one thing we have to remember, this compensation works only at one particular temperature, because even if the one thing is that the bias currents are not exactly equal, that is one problem. That is this current and this current are not equal. Even if they are equal at one temperature, they are not equal at all other temperatures. So, this compensation to be looked only with this approximation, that they may not be exactly come to 0 at all temperatures, there can be a error. So, we discuss this more about this in the next class. Thank you.